On the board, I have the definition of Avogadro's law and also the definition of what STP is. What is Avogadro's law? It is basically, it says that I forgot the T, at the same temperature and pressure, equal volumes of all gases contain the same number of moles. Okay, you take that, and then from that, you get the concept of STP. What is STP? Well, 1 mole of an ideal gas occupies 22.4 liters at STP. What is STP? That's standard temperature and pressure. Standard temperature is 273 Kelvin, which is 0 degrees Celsius. Standard pressure is 1 atmosphere. How are we going to use this? We're going to use it quite a bit in lots of different stoichiometry problems, and I'm going to show you a couple of at least one example of that in the next stoichiometry problem. Okay, remember, anytime a problem says this was measured at STP, they've given you the pressure and the temperature. What's the pressure? 1 atmosphere. What's the temperature? 0 degrees Celsius or 273 Kelvin. Okay, so let's do our first gas stoichiometry problem and introduce the concept of STP in it. Okay. And again, what is gas stoichiometry? Well, you have a reaction, you have to have a balanced equation, and then you're going to probably be asked to measure either the volume or the moles or the temperature or the pressure of the gas. Okay, and usually you use either ideal gas law or you use this STP relationship, which is basically 1 mole of a gas at STP occupies 22.4 liters. All right, so let's see what this problem gives us. I've got a decomposition of potassium chlorate. I've got potassium chlorate will decompose to form potassium chloride and oxygen. We're going to balance the equation, put a 3 here, put a 2 here, put a 2 here. Decomposition, I'm going to put a little triangle, which means there's heat and I have to have a catalyst. And, all right, so I'm going to decompose potassium chloride. 2 moles of potassium chloride will give you 2 moles of potassium chloride and 3 moles of oxygen gas. And the question is, what volume of oxygen measured at STP, again, red flag. The minute you see STP, what does that mean? It means that the pressure is 1 atmosphere and the temperature is 0 degrees Celsius or 273 Kelvin. Okay, so what volume of oxygen measured at STP can be produced by, can be produced by the decomposition of 120 grams of potassium chlorate. Okay, let's see here. I want the 0 of the 120 to be significant. I'm just going to put a decimal here, but really I should write 1.20 times 10 to the second power just to make sure that I get my 3 sig figs at the end. Okay, good. The only way I can relate potassium chlorate to oxygen is through the coefficients of the balanced chemical equation, molar ratio, just like we did in stoichiometry in chapter 4 and in chapter 3. All right, this is gas stoichiometry. You could put that as a nice little heading for you guys, gas stoichiometry with an STP twist. Okay, all right, so we're going to start off with our 120 grams of potassium chlorate. Obviously, the first step if we're given grams, convert them to moles. So we need the molar mass of potassium chlorate. I have it written down somewhere over here as 122.55. I have a lot of sig figs. So 1 mole of KClO3 is 122.55 grams of potassium chlorate. How did I get the molar mass? I don't think I have to repeat that for you guys anymore, but you just add up all the masses, 1 potassium, 1 chlorine, and 3 oxygens, and you get this. All right, so that we're done with. Okay, now that we have moles of potassium chlorate, we can now relate the potassium chlorate to the oxygen using the molar ratio. So then you would go 2 moles of KClO3 will produce 3 moles of oxygen. Okay? This is our molar ratio. Simple enough. Now we have moles of oxygen. And what do they want? They want volume of oxygen. Since we're at STP, we're allowed to use that relationship that says 1 mole of oxygen, 1 mole of any gas, in fact, at STP, occupies 22.4 liters. That's when you are allowed to use that. So we're going to put it right over here. We're going to say 1 mole of oxygen will occupy 22.4 liters. Look how beautiful it is, guys. Everything cancels so nicely, and you end up with your volume in liters. So you get your calculator and you plug it all in. 120 divided by 122.55 times 3 divided by 2 times 3 divided by 2 times 22.4, and you, let's see if I'm doing this correctly here. Yep, I can barely read it. Is it 32.9? That's what I have. Let me try it one more time. 120 divided by 122.55 times 3 divided by 2 times 22.4. Yep, 32.9 liters. Perfect. I don't know why I second guessed myself. There you go. Okay, so what I just did in this example was I did a stoichiometry problem using all of the rules of stoichiometry we've done before. And then once we got to the molar ratio part, you know how sometimes after the molar ratio we then convert moles to grams, or we use molarity to convert moles to volume based from the molarity information. Well, here we converted moles to volume because this is a gas using the STP relationship. Okay, 1 mole of any gas always occupies 22.4 liters if it's at STP. Okay, so now let's do another gas stoichiometry problem, but it's not at STP. Let's do one where I give you the temperature, I give you the pressure. It's not at STP, it's still gas stoichiometry, so still the same heading, guys. All right, here it is. Okay, so you've got this equation. Calcium carbonate is going to react with hydrochloric acid to produce calcium chloride and water and CO2. Why? Because when we do the double replacement or the exchange, the H with the CO3 becomes H2CO3. Remember how I told you then that when you get carbonic acid as a product, it always breaks down to form water and carbon dioxide. So you get that. And we're going to balance the equation. We'll put a 2 here. And I think we are good. All right. So basically what this problem says is that when a 2-liter bottle of concentrated hydrochloric acid was spilled all over the lab, you had to use 1.2 kilograms of calcium carbonate to clean it up, basically to neutralize the spill. And the question is, what volume of carbon dioxide was produced when in this reaction at 735 millimeters of mercury and 20 degrees Celsius. So you can see here that we have to have a stoichiometry problem because we've been given information about the calcium carbonate and we want to know how much carbon dioxide is being produced. The problem starts off by saying when a 2-liter bottle of concentrated HCl was spilled, you don't use that information for anything. It's just basically saying, okay, you created a mess, you dropped a whole bunch of HCl, you need to neutralize it by adding calcium carbonate. Well, how much carbon dioxide are you going to get? So I guess we needed the HCl to write our balanced equation. Okay, so we want to relate calcium carbonate to carbon dioxide and ignore everybody else. Notice here, this is not STP. So once we get the moles of CO2, so we're going to do stoichiometry till we get the moles of CO2. Once we get the moles of CO2, what are we going to do with that? We're going to plug it into the ideal gas law using this pressure and this temperature. We have to make sure we convert that to atmospheres, convert that to Kelvin. We'll have moles, we'll have pressure, we'll have R, we'll have temperature. We'll be able to get the volume, okay? So first, stoichiometry. So 1,200 grams of calcium carbonate, and I need the molar mass. 1 mole of calcium carbonate. Crunch the numbers here. Okay, calcium's 40, carbon's 12, oxygen's 16, and I have 3 of them, so that's 100 grams. It's molar mass of calcium carbonate. Okay, for every 1 mole of calcium carbonate, we're going to be producing 1 mole of CO2. 1 mole of calcium carbonate, you'll produce 1 mole of carbon dioxide. Okay, so 1,200 divided by 100 is 12 moles of CO2. Okay, you guys know where I got the 1,200 from. That was 1.2 kilograms. I just turned it into grams so that I could use molar mass. Okay, so I have 12 moles of CO2. What do? I need PV equals nRT. All right. I have my pressure at 735 millimeters of mercury. I want to make sure I turn that into atmospheres. So this pressure is going to be 735 millimeters of mercury divided by 760 because 1 mole, not 1 mole, 1 atmosphere is 760 millimeters of mercury. We all know that. Volume is my unknown. That's my X. My N is 12 moles. My R is 0.0821 atmosphere liter over mole Kelvin. And my temperature is 20 plus 273, which is 293 Kelvin. Okay, so I can plug everything in, manipulate the equation, and solve for solve for V. We want to find volume. All right, so I'm going to go ahead and do that. 12 times 0.0821 times 293, okay, divided by, I'm going to open parentheses, 735 divided by 760, close parentheses, equals, and I have 298 liters. But I need 2 sig figs. So the 8 is going to round the 9 to a 10. So we end up with 3.0 times 10 to the second liters. If we're paying attention to sig figs, and we always should, it's going to be 300 liters. And I'm making it as 2 sig figs because this is 2 sig figs. Okay, so what I just showed you in this video was gas stoichiometry using STP with one problem and then using the ideal gas law with this second one. All right, so in our next video, we will get started with Dalton's law of partial pressure.